Oh, that was a slow start. All right, welcome to section 5.3, graphs of polynomial functions. So in this section, we're going to recognize characteristics of graphs of polynomial functions. We're going to use factoring to find their zeros. We're going to identify zeros and multiplicities. We're going to talk again about end behavior. We have talked about that before. We're going to talk about that again. We're also going to talk again about degree and turning points, and then we're going to do some sketching graphs of polynomial functions. All right, so let's get started. So polynomial functions that have degree greater than or equal to 2 are graphs with no sharp corners. Okay, we call them smooth and continuous curves, because if you graph them with your pencil, you never have to lift it up. So we want them smooth, we want them continuous. So let's look at these 4 examples and see if we can pick out which ones of these are polynomial functions and which ones are not. Well, the first one is a polynomial function, so this is a yes. Let's actually get a pen so I can write there. Yes. Smooth continuous curve. This guy is a no. We should recognize that as an absolute value. This guy is a yes. Again, another smooth continuous curve. And this guy is a no because of this big gap right here. Can't have big gaps in polynomial functions. All right, so let's talk about the factored form of a polynomial function. So this equation right here that gives you the factored form of a polynomial function is pretty hard to read, but we're going to work through it and get used to it. So it says a polynomial function is of the form p of x equals a, x minus r1 to the m1, x minus r2 to the m2, dot, 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 x minus r sub n to the mn. So let's work through this a little bit with an example. First of all, the a out here is going to be your leading coefficient, just like when we've talked about with quadratics and other degree polynomials. Each x minus r is a linear factor, and each r represents a root of the polynomial. Each m represents the multiplicity or the exponent on that factor. So let's look at an example. Let's look at the example p of x equals 2, x minus 1x plus 2. So in this case, we have two r's, right? This is like x minus r1 to the m1, x minus r2 to the m2, right? So that's the shortened version. We know this is a polynomial that only has two linear factors. So first off, let's answer some questions about it. That's not what I meant to do. I meant to do this. Let's answer, what is the leading coefficient? Remember, we always look at a. In this case, the leading coefficient a is 2. Leading coefficient of 2. What is the degree of this polynomial? Well, looking at the graph, we should right away be able to see this is a degree 2, right? But another way you can do this is you add up all your multiplicities. Well, in this case, our m1 is equal to 1, right? Because there's only a power of 1 on each of these guys. And our m2 is also equal to 1. 1 plus 1 equals 2. So this is, again, a degree 2 polynomial. And what are the roots? Roots, zeros, horizontal intercepts, these are all the same things. We use all 3 terms, and different books and different people will use these terms interchangeably, so I'm going to use all 3 of them. So we want to look at the zeros, or the roots, or the horizontal intercepts of this polynomial equation. And the way to find those is to look at the r's. Let's rewrite our equation, our polynomial equation over here. It's p of x equals 2 times x minus 1x plus 1. Well, this guy is going to be equal to 0. That's going to be the zeros of our equation. Our horizontal intercepts are going to happen y equals 0. Well, if we look at this equation, when is this going to equal 0? Well, 2 can never be equal to 0, so that guy's not going to equal 0. But x minus 1 equals 0 when x is 1, and x plus 1 equals 0 is 0 when x equals minus 1, which are exactly our r values from the original problem. So if we go back up and match up our r values, what is up with this today? Okay. Go back up. Our r values, remember, it's x minus r1, so r1 is 1, and r2 is, we need to write this as x minus negative 1. Sorry about the beeping in the background there. Is it going to stop beeping? Yes. Okay, x minus 1, so this r2 value is negative 1. So r1 in this case is 1, r2 is negative 1, and that's exactly what we got when we solved this equation using the zero product property that we all learned when we studied quadratics, or hopefully we learned when we studied quadratics. So what are my roots? X equal to 1 and x equal to negative 1, and that's verified also by looking at our graph and realizing it crosses the x-axis at x equals negative 1 and x equals positive 1. All right, so let's try a little bit harder one. This is basically what I just said before, things to know. The factors tell us about the horizontal intercepts. If x minus r1 is a factor, then r1 is a root, right? If you add up your multiplicities, you'll get the degree of the polynomial. So let's try a little bit more complicated polynomial this time. All right, g of x equals x times x plus 1 squared times x minus 3 to the 4th times x minus 1 cubed. And actually, let's go ahead and rewrite that right here. And we're going to list all their roots and multiplicities, so we're going to rewrite them all as x minus something. So I'm going to write this as x minus 0. I know, tricky, right? And x minus negative 1 squared, x minus 3 to the 4th, x minus 1 cubed. So all my roots are going to be x equals 0 is my first root, x equals negative 1 is my second root, and that one has multiplicity 2. X equals 3 has multiplicity 4, and x equals 1 has multiplicity 3. Looking at the powers for each of those, this one has multiplicity 1. You actually don't usually have to say that, but I'll just say that because this is to the first power, right? So x equals 0, negative 1, 3, and 1, and there's their multiplicities. All right, we found all the roots, we found the multiplicities. What is the degree of this polynomial? Well, we want to add up all these multiplicities to get the degree, right? Degree. So I'm just going to add across. 1 plus 2 plus 4 plus 3 is 10. So this is going to be a degree 10 polynomial. Find the vertical intercept. Do we remember how to find the vertical intercept? In a previous video, I said how to always find it. And remember, the vertical intercept is always when x is 0, right? We're not left or right. So to find the vertical intercept, this is part C. I guess this was sort of part A. This is part B. To find the vertical intercept, you're going to plug in 0 for x. G of 0 equals 0 times 0 plus 1 squared times 0 minus 3 to the 4th times 0 minus 1 cubed. And I'm not even bothered to figure that out because if I multiply 0 by something, I'm going to get 0. So my vertical intercept is the point 0, 0, which is also a horizontal intercept in this example. What is the end behavior of g of x? What is the end behavior of g of x? Well, remember when we talked about looking at the end behavior of polynomials, we always said we had to look at the leading coefficient and the highest degree. Well, this is going to be a degree 10 polynomial. If we wanted to, we could multiply this all out. I don't really want to. But I do know that it's going to be a degree 10. The highest degree is going to be 10. So that means it's an even number. So 10 is even. So this guy is going to behave like either x squared or minus x squared. So it's going to behave like x squared or minus x squared. Which one is it going to be? Remember, we have to look at the leading coefficient. Well, in this case, the leading coefficient is sitting here quietly, not saying anything. It's equal to 1 in this case. So that is a positive number. So it's going to look like x squared, right? Not minus x squared. A is positive, so this guy's end behavior is going to look like x squared. Remember what x squared looks like? This is just up in my thoughts over here. So this guy's going to go to, as x goes to I don't want that x there. As x goes to minus infinity, g of x is going to go to infinity. And as x goes to positive infinity, g of x is going to go to infinity. And now our final step is to sketch a good enough graph by hand. So really, this is a sketch. This is not drawing a careful graph. This is a sketch. And the way I'm going to do this is I'm going to start by looking at all my different zeros. Well, I have x equals 0 as x intercept, horizontal intercept. I have x equal to negative 1, and that's a multiplicity 2. I'll remember that in a second. 1, 2, 3, x equals 3, that's a multiplicity 4, and x equals 1, that's a multiplicity 3. So 0, 1, 2, 3. So x equals negative 1, 3, 1, and 0. I don't want to miss any there. All right, so what goes on in between these? Well, we know the end behavior. So this is, remember, it's very much sketching a graph. So I know that as we go to negative infinity, we're going to go up on either end, right? Because I know it has to look like x squared in the long run. And I know it never crosses the x-axis again because there are no other horizontal intercepts. So I know what it has to do from negative 1 to negative infinity and 3 to positive infinity. More or less looks like that. All right, at x equal to 0, we have a multiplicity 1. So multiplicity 1, this looks like a line, right? Multiplicity 1 is like a line. It's a linear term. So that means I'm just going to go through the axis. Now let's go to our next one. At x equal to -1. Oh, whoops, I did that the wrong spot, didn't I? Dang it. I was looking at the wrong one. Okay, edit that out of the video. Start back. Start now. All right, so when I go through the roots here, I'm going to go through them from smallest to largest. So the first one I'm actually going to look at, let me switch colors really quick here. The first one I'm actually going to look at is my first smallest root. I'm going to look at this guy first. X equal to -1, and this one has multiplicity 2. When you have a multiplicity that's even, it's going to behave like x squared. So it's going to come down and go back up because we're squaring each of the terms. So we know that around here, it's going to come back and square back up like a squared term. All right, so let's go to our next one, x equals 0, so that one's checked off, has multiplicity 1. So we know it starts up here, and multiplicity 1 behaves like a line, okay? It behaves like a line. So I'm going to go through the 0 one like a line. So I'm just going to connect the dots here. X equal 1 has multiplicity 3. That means it's going to go through like x cubed. Remember, x cubed looks like that a little bit. So I'm going to have to come down a little bit, and then I'm going to go flat and come back up. That's what's going to look like at a multiplicity 3. And even multiplicities act like x squared, so this one's going to be a down back up again. Okay, is this a great graph? No, this is definitely not a great graph, but this is a sketch of what's happening. I have my end behavior going to infinity, right? I have my two even multiplicity roots that are behaving like coming down, touching, and going back up. And I have my odd multiplicity roots. These are my even ones, even multiplicity. And then I have my odd multiplicity roots which cross through the x-axis. All right, so that's my good enough sketch. All right, that's it for this video.